The Martian deep freeze, the polar regions. These fascinating places hold the key to an important part of the evolution of the Martian surface. They are the cold traps for an enormous amount of frozen water, carbon dioxide, and other volatiles. Volatiles have shaped the surface in the polar regions as well as periodically affecting the entire surface of Mars. Periodic changes in climate control the deposition, erosion, and stability of volatiles in this region. As on Earth, the poles of Mars receive less sunlight and as a result are colder than its equator. Mars is inclined at about 25 degrees on its axis of rotation, similar to the Earth's 23.5 degree tilt, and as a result has seasons. But Mars is in a highly elliptical orbit that changes its distance from the Sun considerably during the year. This makes the duration and temperatures of each season different from the others. Remarkably, the situation changes periodically. The gravitational pull from other solar system bodies tugs at the orbit and axis of Mars, continuously changing its characteristics. Changes in astronomical characteristics have dramatic effects on solar heating of the surface, especially in the polar regions. Heating controls the stability of frozen volatiles stored in the polar regions of Mars, and also when the season of maximum dust storm activity occurs. Dust storms are particularly important because they provide airborne dust grains for nucleation sites for condensation of frost from the atmosphere. Thick dust clouds can shade the surface from solar heating. There is considerable evidence that an enormous inventory of water and carbon dioxide is stored at the polar regions of Mars. The most obvious storage site is in its polar ice caps, though they only contain a small portion of the total inventory of Mars. Most evidence suggests that an enormous reservoir of ground ice is locked up in the regolith at high latitudes. Steve Clifford summarized the general view of most Mars scientists, saying, "Evidence suggests that Mars is water-rich and may store the equivalent of a global ocean of water of about 0.5 to 1 kilometer deep as ground ice and groundwater within its crust." On Mars, winter temperatures fall below the frost point of both water and carbon dioxide above about 80 degree latitude. The cold temperatures allow carbon dioxide and water vapor from the atmosphere to condense on the Martian surface. About 30 degrees latitude, average surface temperatures are too warm for surface frost, but are low enough for ground ice to be stable. A huge amount of volatile components must be trapped on mineral grains. Under warm, wet conditions, some mineral grains readily absorb volatiles either on their surfaces or by locking into their structures. Releasing these volatiles back into the Martian atmosphere is difficult and requires unusual conditions. In the lower latitudes, conditions are very different. Surface and subsurface temperatures are always too warm for ice or carbon dioxide to be stable. Sublimation and diffusion processes quickly desiccate the upper part of the Martian regolith in this region, leaving it dry down to a depth of several hundred meters. Volatiles that evaporate from this region quickly migrate to the planet's cold traps, the polar regions. Although the loss rate of such volatiles from the regolith is easily calculated, recent observations of small, young channels suggest that Mars is a planet with an active hydrologic cycle. It is constantly being recharged even under current conditions. Because the polar regions are the planet's cold traps, they must play an important role in this cycle. And that's the Martian deep freeze, the polar regions. Have a great day.